Assalamualaikum and hi everyone. So finally we have come to the very final chapter, that is partial differential equation. Okay, so this one is going to be your last question in the final exam. Contribute, I think 20 marks, okay, just for this chapter. Okay, 15 to 20 marks only for this chapter. Okay, so let us start with some terminologies first. Okay, so what is the PDE? Okay, so the PDE is basically a differential equation that consists of more than one independent variable. Okay, so in contrast to the PDE is the ODE. Okay, what we have discussed so far is normally on the ODE. Okay, so we have first chapter, second chapter, little bit of third chapter at the last part of the chapter. All of them involve the ODE. Okay, so ODE only involve one independent variable. So you have a function of y that depends on t only or depends on x only. Okay, but for the PDE, it is equation that depends on more than one independent. Okay, so for example, we have u here, u in terms of x and y. Okay, so in this case, we can see that x and y are the independent variable. So u depends on two independent variable. Okay, so it is again it is called the differential. Okay, because in the equation it contains at least one derivative. Okay, that implies the differential equation. Okay, so the sum of the partial derivative that involved given here. So del u del x, okay, or also can be written in terms of u subscript x. Okay, uxx, okay, for the second derivative. Okay, uxy meaning that we have second derivative. Okay, but with respect to y and then with respect to x. Okay, and in this chapter you are going to learn about three types of PDE. Okay, so you have wave equation given in this form. So this is the general wave equation. And then you have the heat equation given here. And then you will have the Laplace equation. Only these three. Okay, only these three. So this one, okay, wave equation in 2D and heat equation in 3D. So the last two here is out of the syllabus. Okay, so we will discuss only these three. Do not worry about the equation. Okay, you are not going to memorize the general form of each equation that we have here. So it will be stated in the problem. Okay, so our focus is to know the method. Okay, the method to solve the PDE. Okay, each of the equation that we have just now. Okay, so the main method that we are going to discuss here is called the method of separation of variable. Okay, so this is the most well-known method, okay, to solve the partial differential equation. Okay, so for discussion, let us consider this heat equation here. Del u del t equals k square, where k is constant, del square u del x square. Okay, so the basic idea of separation of variable methods. Okay, so the solution to the heat equation here, to the equation 1 here, is assumed to be in the form of x times t. Okay, because we know by solving this, if I say solve this equation 1, so meaning that, okay, you need to get what is u, just like what you have in chapter 1 and chapter 2. You have the differential equation given, so your task is to get y of x at the end. Okay, so the same thing here, you were given a function, okay, a differential equation in terms of u and t, okay, also in terms of x here. So by solving this, you are actually finding the equation for the u in terms of x and t in this case, because the PDE involve more than one independent. So in this case, we have t and x. So the final answer should be in the form of x times t. All right. So the x here, the capital X here is a function of x, okay, and the capital T here is a function of time. Okay, so the small x here is the spatial spatial coordinate, and t, of course, for the time. Okay, so by separating the variables x and t, okay, we are actually reduce the problem from the PDE, okay, to be the ODE. Okay, so let's look how it works. Okay, so first, okay, again, the basic idea is to assume the solution is in the form of x times t. Okay, so let's denote as equation 3 here. So by the equation 2 here, by the equation 1 here, we have del u del t. Del u del t means derivative of u respect to t. Okay, so by this equation, if we find del u del t, meaning that we differentiate t only. Okay, and you should know that by the partial derivative, okay, meaning that if you want to differentiate respect to t, the other variable, which is x, will regard as constant. So basically here, you differentiate respect to t only. Okay, so that's why we have here x times t prime. So similarly for the uxx here, so del square u del x square, meaning that the second derivative of u with respect to x. So from here, we differentiate u here respect to x twice. Okay, so we have here uxx, okay, meaning that we differentiate the x here, okay, 2 times. So we have x double prime. So t just follows here because we treat the t here as constant. Okay, so by these two, okay, and then when we put in this equation here, so del u del t becomes this one. Okay, so in short, I can write as xt prime equals to the k square, and this is uxx, okay, which can be rearranged as this one. Okay, so basically just separating the variables. All terms that involve the x should be on the left, and the remaining should be on the right. So we have equation 5 here, just the arrangement only. Okay. All right, so based on the equation 5 here, okay, so we know that the left-hand side here will be equals to right-hand side if, okay, both functions are constant. Otherwise, they are not equal to each other, because at the left-hand side, they are all in terms of x, and at the right-hand side, they are all in terms of t. So they are not going to be equivalent, okay, if they are not constant. Okay, I hope you can get that. Okay, so it means that x double prime over x equals to the t prime over t here is actually equals constant, which we denote as lambda. Okay, otherwise it is not equivalent. Okay, because left hand side is a function of x and the right hand side, okay, is a function of t. Okay, they will never be equivalent to each other if they are not constant. Okay, so in order to make the equation 5 here is valid, they need to be a constant, okay, which we denote as, again, lambda. Okay, so by this equation now, we can construct two equations. Okay, so if I cover up this one, okay, so I have x double prime over x equals lambda. Okay, which can be rearranged as equation 6 here. Okay, so similarly, if I close this one, then t prime over k square t equals lambda, which can be rearranged as equation 7. Okay, so we can see that equation 6 and 7 now is the ODE. Initially, we have the PDE. Okay, by separating the variables here and there, we come out with the equation 6 and 7, which are ordinary differential equations. Okay, there are ODE because each one of them, okay, depends on single independent variable only. Okay, you can see equation 6 only involve the x. Equation 7 only involve the t. Okay, so we have reduced the PDE in one, okay, to be two ODEs. Right? So if we go back to our first assumption here, so this is our final answer should be u is equal to x times t. Okay, so now I want you to refer to equation 6 and 7. Okay, so by equation 6, if you solve equation 6, you are supposed to get x in terms of small x. If you solve equation 7, then you will get what is t in terms of small t. So with the solutions from 6 and 7, you are going to put back in equation 3 here to the solution here. That will be your final answer. Okay, so those are the basic steps in separation of variables method. Okay, and the solution will be proceeded, okay, by applying the boundary conditions and initial conditions, okay, so that we can find the value of the constant involved, okay, in solving these two equations here. All right, so for exercise here, let's try to reduce the following PDE to two ODEs by separation of variables method. Okay, so let's do for wave equation here. So for A here, we are going to assume our solution is in the form of x times t of t. Equation 1 here, in short, can be written as UTT equals alpha square UXX. Okay, so from U equals X times T, we find the UTT, meaning that we differentiate U with respect to T twice. Okay, so we have X, so I'll just ignore the small x. Okay, and then we have t double prime because we differentiate u two times with respect to t. So similarly for the uxx, we differentiate x two times, so we have x double prime t. Okay, so when we put back in the equation, we are going to have x t double prime equals alpha square x double prime t. And then by separation of variables, we can have x double prime. So normally we put the derivative, the higher derivative to be at the top. Okay, and then the denominator, okay, with the lower derivative. So x double prime over x, okay, is now t double prime over alpha square t, which is, okay, can be equal to some constant lambda. Okay, so if we rearrange, so x double prime over x equals lambda, so x double prime minus lambda x equal to 0, so this is equation 1, and t double prime minus alpha square t, so somewhere here is lambda equal to 0, so this is equation 2. So from the PDE here, we have reduced to the ODE, okay, the two ODE here, okay, and the full solution, okay, should be longer, okay, but the first step is to reduce the PDE to the ODE, okay, so similar to the Laplace equation here.